basic discussion. I'll be not talking a lot of mathematics also. Basic discussion on nuclear force. What we know about the nuclear force. Okay. Now, before basically we will be studying the deuteron in a more specifically to get a better understanding of nuclear force, and then later on we will talk about various scattering for the two body systems to get again more ideas about nuclear force. But before I start, let us just pause and think about what we know about the nuclear force till now. So, observations. Number one. Now, you see, there are many stable nuclei which are protons. And what does this mean? This means that at short distances, the nuclear force is stronger than Coulomb force. So, many nuclei present, many nuclei are stable, and these nuclei have protons. So, this means in itself that short distance nuclear force is stronger than Coulomb force, since it can overcome the Coulomb repulsion of protons inside the nucleus. Otherwise, nucleus would not exist. This is the first observation. Next observation is that, what did I tell you? That short distances nuclear force is stronger than Coulomb force. Now, just think about the opposite. Why do you think the nuclear force has a short range? So what if, again, where is it? What if nuclear force has infinite range? What do you think will happen? Tell me, students. Anyone? Just tell me the opposite of what we are thinking. What if the nuclear force has infinite range? Then what will happen? As a result, all nucleons everywhere, they will start attracting each other, coming close to each other, and as a result, instead of the variety of world, the world that we live in, we see so many things, right? You see, for example, when you are hearing my lecture right now, you are seeing your smartphone. Some of you are eating as well, some of you are doing something, some of you are sitting on a sofa, on a table and all that. So many things. Now, if nucleus has an infinite force, then so many things, they will just come together. So much variety will not exist. And all these things will come close together, and we will have a very big nucleus, a lump of nucleus. As a result, no life. So in a way, we are very lucky that nuclear force has short range. Life will not exist. Okay, just think about it. So much variety only because it has short range. Otherwise, everything will come close together and form a big nucleus. Nothing else, no variety. Such a dull life. That's why we have got a short range. Okay, but this is important. You must understand. What you are observing sometimes means that what you are not observing also has meaning. And this is what I am telling you. Okay, third observation. Now you see, at long distances, what long distances? My arm's length? No. At long distances, say of the order of atomic sizes, that is angstrom or 10 to the power minus 10 meter distances, the nuclear force is negligible. Since the interactions between the various nuclei inside a molecule can be understood solely on the basis of Coulomb force. You will later on study molecular spectroscopy, and trust me, nowhere in molecular spectroscopy you will be talking about the effect of nuclear force. Why? Nuclear force is not there. Of course it is there, but see, at distances where molecules or atoms exist or they interact with themselves, atomic distances, angstrom order, the effect of nuclear force is zero. Again, we are so lucky. Okay. Now, fourth observation. Write down these observations in your copies later on, because I'll be asking you in examination. This is what will I tell you, a very important part, also one of my favorite parts. The various information that we know about nuclear force just before studying it more quantitatively. Now, the fourth observation is that, you see, for stable nuclei with mass greater than 10, what do you observe? You observe that the binding energy per nucleon is almost constant. This is number one. This is number one observation. Number two observation you observe is that for the nuclei, they generally follow R equal to R0 into 8 to the power 1/3 nature. This means that they have constant density. So again, binding energy per nucleon constant, and again constant density. These two constancy, density and binding energy per nucleon, they again show that the nuclear force is saturated. Okay. Now, what do we know about nuclear force? Yes? Okay, so yes, number 5. Now you see, there is no evidence from atomic structure that electrons feel the nuclear force. This is also important. Okay, so this is what I am saying. There is no evidence from atomic structure saying that electrons, they feel the nuclear force. We don't have any such observation, which is good again. So they are good observations, otherwise my system will become even more complicated. Right. Okay, so let me again recapitulate. So basically we are talking about trivial observations, right? Before we formally start the study of deuteron and two-body scattering. Now, the first observation basically was that is regarding the existence of stable nuclei, and they have lots of protons. So, at short distances, the nuclear force, yes, the nuclear force is greater than the Coulomb force. Next, what if nuclear force has infinite range? Then there will be a different world, only a single big nucleus. So of course everything that we know will never exist. And then we observe that at long distances, say of the order of atomic sizes, NF is, nuclear force is negligible. So at these sizes, nuclear force is negligible. Right? And the fourth observation is that for nuclei greater than, mass greater than, atomic number greater than 10 or so, we have the binding energy per nucleon, which is approximately constant, and also the nuclei generally follow this radius versus mass number relation. Okay, and so both this constancy means that nuclear force is saturated. And number 5 was basically the fact that there is no evidence from atomic structure which says that electrons feel nuclear force. Now the story doesn't end over here. We have got two more very interesting observations. Let me talk about them. So till now we have covered 5. So the sixth one is basically regarding the strength of the nuclear force itself. You see, nuclear force is very much strong. And how do we know? Well, look into the values of binding energy. Okay, so binding energy of nuclei, and basically how much is this? So basically binding energy per nucleon is of the order of 8 MeV. This is a very large value. Why? Because if you compare it with the case of atomic physics, atoms, there the binding energy is of the order of electron volt to K electron volt, but here it is much larger. Look at the unit MeV. This suggests that the nuclear force, though its range may be small, it is very strong in its range of operation, in its limited region of working. Okay, fine. Now lastly, let us talk about two body systems. So basically, if we have two body, or let us consider nucleus containing two nucleons only. Now what are the possibilities? We can have either a proton-proton system, or a neutron-neutron system, or a proton-neutron system. This is basically your deuteron. Now interestingly, these two don't exist, whereas deuteron is stable. Now the very fact that these two don't exist whereas this exists and is stable, although this is very loosely bound, okay, its binding energy is only approximately 2 MeV or so, although this is loosely bound, but still it exists. So this means that there is something going on with the nuclear force itself. The nuclear force distinguishes between protons and neutrons or so. What do you think? Now you might consider the fact that in this particular case, since there are two protons, so the Coulomb force will be playing a role. Of course it will play a role, but remember, within the range of the nuclear forces, strong interaction is very much stronger, right? Now, okay, you can say that here, now let us consider a different argument. You can say that here the two protons state does not exist, diproton state does not exist because of the Coulomb force. Then what about here? There is no Coulomb force. There is no issue with that. They are two simple neutrons. Then why does this state not exist? This has got to do something with the nature of the nuclear force itself. Whether this is, see, there is another very interesting observation. Number one, here we have Coulomb force present. There is no Coulomb force, but in these two cases we have got like type of nucleons. Like type of nucleons. So nuclear force, of course, it must be different for this scenario compared to the unlike case here. Unlike type nucleon. So you see, just from this very simple observation, whether this proton-neutron system exists and dineutron and diproton don't exist, from here we can say that there has to be something going on with the nuclear force itself. Now we will cover more about this in details when we talk about deuteron.